Okay, when you have parametric equations, the calculus that you're going to perform is a little bit different. Same concept, but a little bit different. Your homework is right here, and we're in 10.3. So the parametric form, remember you have x is a function of your parameter and y is a function of your parameter. So when you take the derivative, you're going to take the derivative of y with respect to the parameter and the derivative of x with respect to the parameter, and dy dx is just dy over dx, as long as you're not dividing by 0. For example, x is given as 2t and y is given as 4 minus t squared, then the derivative of x is 2 and the derivative of y is minus 2t. So dy dx is minus 2t divided by 2, and you get minus t. Your parameter is not always t. In this case, we have parametric equations where theta is the parameter. Now, as you move through this chapter, we're going to be switching to a different way of graphing called polar coordinates, which is going to have theta in it, but it's not going to have x and y. So you need to keep in mind that anytime you see x and y, you know that you're using parametric equations on the xy axis. This is not polar just because there's a theta in there, and I'll say that again about a dozen times until you're sick of it. So take the derivative of x with respect to theta, you get minus cosine. Take the derivative of y with respect to theta, you get minus 2 sine. So dy dx is minus 2 sine divided by minus cosine, and you get 2 tangent. Okay, higher order derivatives. This looks awful, but it really isn't that bad, okay? If you're going to take the second derivative with respect to x, remember you already took one derivative with respect to x. So now you're taking the derivative of the derivative with respect to x, right? So what did we do when we took the first derivative? We put dy with respect to the parameter over dx with respect to the parameter. So we're just going to do the same thing here. We're going to take the derivative of what we just found with respect to t right here, and then divide that by dx dt. So every time you take another derivative, you're taking the derivative of the previous derivative with respect to t, and then dividing by another dx dt. So the second derivative is the derivative of the first derivative divided by dx dt. The third derivative, and let me fix that right there, the third derivative with respect to x 3 times is going to be the derivative of the second that we just found in the previous step divided by another dx dt, and you can keep going in that manner. So looking back at the equations that we had in example 1, the derivative of y with respect to with dy dx was minus t, and dx dt was 2. So the second derivative will be the derivative of the dy dx with respect to t divided by dx dt. So this is a minus 1, and there's your minus half is your second derivative. Example 2 from before, we had dy dx, the final derivative was 2 tangents, and the dx dt was minus theta, minus cosine theta. So the second derivative is the derivative of this with respect to theta divided by this. So derivative of 2 tan is 2 secant squared divided by dx dt, and that is going to give me minus 2 secant cubed. Now, new example, x is 6t squared, so his derivative with respect to t is 12t. Y is 2t cubed, its derivative will be 6t squared. So dx dt is the dy over the dx. Simplify and you get t over 2. So the second derivative is going to be the derivative of t over 2, which is just a half, divided by the dx dt. So we have 1/2 divided by 12t is going to give us 1 over 24t. All right, using parametric equations and finding arc length. Remember when we found arc length before, that it was the integral of the square root of 1 plus the derivative squared. We did that early on when we were rotating about an axis. So here's your arc length in non-parametric form. This is y as a function of x. So we took the derivative, we squared it, added 1 to it, put it under the radical. Now, h prime is dy dx, right? Because y was a function of x. So if we've got dy dx squared and now we're in parametric form, then that's dy dt on the top and dx dt on the bottom. They're both squared. Now if we get a common denominator, we have this. If we take the square root of the top and the square root of the bottom, then the bottom is just dx dt with no root. Now, this gives me the derivative of x squared plus the derivative of y squared under the radical still. And when I invert this and multiply it, the dt comes to the top and the dx's cancel. And here is my parametric form of arc length, the square root of the sum of the squares of the derivatives. Make sure that on the interval a to b that the curve does not cross itself. When we're using these parametric equations, we're going to get all kinds of curlicues and loop-de-loops and flowers and things like that. So we have to make sure that the curve doesn't cross itself on this interval to get the arc length. Okay, let's take the third example that we used and find the arc length of this curve for t between 1 and 4. So we're going to take the derivative of each of them. We're going to square each of those derivatives, add them together under the radical, and integrate from t equals 1 to t equals 4 with respect to t. So you square this, you get 144t squared. Square this, you get 36t to the 4th. So we have this, and I see that I can factor out a 36t squared. And now because this is multiplication, I can take the square root of this factor and the square root of that factor, and I'm left with 4 plus t squared under the radical times t dt. Now, if I set the inside equal to u here, let me write this down. I can say that u is the stuff in the parentheses, and du is the derivative of that, 2t dt. So I had the t and I had the dt, so I just multiplied by 2 over 2. So 2 inside and a 2 outside, that gives me a 3 on the outside, and it's u to the 1/2 du. So add 1 to the power, divide by the power. When you flip this over, the 3's cancel. You're left with 2 on the top. Plug in the 4 and you get 4 plus 16. Plug in the 1. You get 4 plus 1. This is a 20 and this is a 5. But there's common factor there, right? 20 is 5 times 4. Both of those values are being raised to the 3/2. So I'm going to factor out the 5 to the 3/2. I'll be left with 4 to the 3/2 minus 1, which gives me a factor of 7. Now 5 to the 3/2 is just a whole 5 and a 5 to the 1/2. So 2 times 5 times 7 gives me 70. The square root of 5 is right there. Okay, also remember before that when we took that curve and rotated it about an axis, we created a surface. and we could find the arc length of that surface, capital S. And remember, it was just 2 pi r, and the arc length was like the height. So 2 pi rh, we're just plugging that in, if you can remember that. So we were on an interval from A to B. We have the radius, or the distance of the curve, from the axis of rotation times the arc length component that we found before. So if you're rotating about the x-axis, now that we're in parametric form, the arc length is now this. We had dx dt squared, dy dt squared. But if we're rotating about the x-axis, think about it. If we're about the x-axis, the radius is just the y value. So this is not a y that we're plugging in. This is the formula, the parametric form of y. So this is a function of t. So are these derivatives. If we're rotating about the y-axis, our radius is x. So you practice doing arc length, and then to do surface area, you just have a 2t and either the x or the y, depending on which direction you're rotating. Okay, let's try this. Here's our equations. My dx dt is just a 1. dy dt is just a 2, negative 2. We're going to find the surface area from 0 to 2 if it's rotated first about the x-axis. So if you're rotating about the x-axis, you have a y for your radius. It's this squared plus this squared added together under the radical. In this case, they're just numbers. 1 squared plus 4 is 5 under the radical. The y is 4 minus 2t, and it's just a straight up simple power rule integral evaluated, and we get this. If we're rotating about the y-axis, we have to plug in the x, and x is just t. So there's your x. This right here is the square root of 5. We already figured that out. Integrate t squared over 2, evaluate, and you get just 2 minus 0. And there's your final answer. These do get complicated, and sometimes you having that radius in there, if you've got sines and cosines or higher powers and stuff, it'll help you be able to integrate a square root. Sometimes when you're just finding the arc length, you can't do the integral, or it's very difficult. So practice your homework, because it builds and it gets a little bit worse and worse as you go. One thing that's going to be really, 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 really important for you to do is to be able to figure out where your curve crosses itself and where you have vertical or horizontal tangents. Finding those places is going to really make graphing easier, and you will be graphing these things pretty soon. So, finding points of vertical and horizontal tangency. If you have, hold on, if you've got some crazy thing like that, vertical tangents are where, let me do that again. Vertical tangents will be where dy dt, excuse me, is equal to 0. Horizontal tangents will be where, I'm sorry, I said that wrong. Vertical tangents are where dy dx is undefined, so it's where dx dt equals 0. Oh, I've got it written down. Vertical tangents are where dx dt equals 0, and horizontal tangents are where dy dt equals 0. So finding the vertical tangents, you're just setting the x derivative equal to 0, and you can see that that's where your curve is approaching vertical. Setting dy dt equal to 0 gives you the horizontal tangents that you're used to finding. And there are going to be a lot of them when you're graphing something like a curlicue. Now, this particular problem is not this, okay? So this particular problem that's written down right here, if you eliminate that parameter here, t squared equals x, so y, oh, I can't just do that, can I? Y equals 4 root x minus x, which is not so pretty, huh? But looking back at the parametric form of the equations, we see that x equals t squared, so x is always positive. That takes care of the domain restrictions here. And it's not going to look like this picture that I drew. This looks like something with trig functions in it. Okay, so vertical tangents are where the y derivative equals 0. I'm sorry, the x derivative equals 0. So you set this equal to 0 and you just get t equals 0. Well, if you take t equals 0 and plug it in for the x and the y, you get the point where that tangent happens. Horizontal tangents are where dy dt equals 0. So we set this equal to 0 and we get t equals 2. Plug that in for the x and the y. Here's 2 squared and here's 4 times 2 minus 2 squared equals 4. So we have those points. So let's see if we can graph this thing. Let me erase what I did here and actually work a problem. So from what we've done so far, we already know that we have a point at 0, 0 when t equals 0, and we have a point at 4, 4. We also know that x is always positive, right? And I'm going to do a little chart thingy. Okay, let's start with, say, minus 2, minus 1, 0, 1, 2, and just for good measure, let's see what happens at 3. Okay, for x is t squared, 4, 1, 0, 1, 2, 9. And now for y, I'm going to plug in a negative 2 for y. This is minus 8 minus 4 gives me negative 12. Well, that's off my graph. But at least we know where it's coming from. Plugging in a negative 1, I'm going to get negative 4 minus 1 gives me negative 5. Plugging in a 0, I get 0. Plugging in a 1, 4 minus 1 is 3. 2 gives me 8 minus 4, and 3 gives me 12 minus 9. Oh, it's starting to come back up. Now, remember, we already found that there's a horizontal tangent at 4, 4, and I wrote something down wrong. Look at that. 2 squared is 4. Okay, like I was saying, there's a horizontal tangent at 4, 4. So you can see that the y value is starting at negative and going up to 4, and then it starts to go down again. So that gives me a little bit of an insight into what this graph is going to look like. Sorry. 1, 2, 3, 4, 5. All right. 4, negative 12 is way down here off the thing. And then as the t value increases, I'm moving up to the point 1, negative 5. and then I'm moving to the point 0, 0, and that has a horizontal tangent. So that's going to be almost vertical at that point. Then I'm going from that point to a 1, 3. So you see that curve. Then I'm at the point 4, 4, which has a horizontal tangent. So that's a maximum. And then I'm way over here at the point 9, 3, so it's going that way. Clean this up a little. So you see how this graph, you see the orientation of it, and you can see the vertical tangent here and the horizontal tangent there. Interesting stuff. Now in the last problem, we didn't find any places where that graph intersected itself. Sometimes this isn't very hard. Our tendency is to, because of what we've done in the past, our tendency will be to take the two equations and set them equal to each other, but that doesn't make any sense. If we set the two equations equal to each other, all we'll be doing is finding if there's any points on the line where x and y are equal, and that's not what we need to do. So the best I can tell you is to pick the easiest one, and especially if you have trig functions like sine and cosine. Sine and cosine are bounded between -1 and +1. So you take the easiest one of the equations. In this case, it's x, because the only t is in the cosine. So I know that this cosine is between -1 and +1. That means that the x value is going to be, where this is -1, that's 2 plus x, 2 plus pi, which is the biggest it can ever be. And then where the cosine is -1, +1, you have 2 minus pi. So the smallest x value is at t equals 0, and the largest x values are at minus pi and plus pi. And we're going to just stay in that little area. So finding the place where the curve crosses itself, notice, and there's a graph of it on the next page. So I'm going to start at minus pi because it was one of my important places, and I'm just going to go up a half pi each time. Sometimes, you see how I left a big space here? Sometimes you may have to cram things in. And when you're doing parametric, and especially when we switch to polar, you want to start at one end of the graph and go to the other. You don't want to mix these values up. I started with the smallest that I care about, and I moved through to the largest that I care about because I found maximum and minimum values for one of my variables. So, plugging the minus pi in for x, cosine of minus pi is -1, I get 2 plus pi. Plugging in minus pi over 2, the cosine is 0, so I just get 2. Plugging in a 0, cosine is 1, so I get 2 minus pi. Plugging in the pi over 2, cosine is 0, I have just the 2. Plugging in the pi, cosine is -1 minus a negative gives me 2 plus pi. So sine is a little bit more, the y value is a little more difficult. Plugging in a minus pi, I'm going to get minus 2 pi minus pi times nothing. So it's just 2 pi. Plugging in the minus pi over 2, multiplying by 2, this is minus pi, again, minus pi, this is a -1, so plus pi. Minus pi plus pi gave me a 0. Plugging in the 0, the sign of 0 is 0, the whole thing is 0, boom, we're done. Plugging in pi over 2, that gives me pi. This is a +1, so I'm subtracting pi minus pi I get another 0. And at this point, we found the 2 points where the curve crosses itself, if there's only 2. Sometimes there's more, but we're just going to worry about these 2 guys right here. The point x equals 2, y equals 0 happens twice here. This x value happens twice, but the y values are opposites. So that's going to help us a little bit with the graphing, because now we know that it's going to come back on itself at that point for the 2 different values of t. Now also, it's a little disturbing that I got 3 zeros for y right in a row, but when you see the graph, you'll see that it makes perfect sense. Now I could fill in like pi over 4 or pi over 3, pi over 6. I could do all of them and really build this curve up if I did those things between. And when we get to polar, you're going to have to do that. But we can do it in a very wise way that keeps our numbers easy. And I'll show you that next section. So we have our 2 points where they cross. We have the 2 different values of t. So the slope where t is minus pi over 2 is dy over dx. So the derivative of y is here. The derivative of x is here. I'm going to plug in the minus pi over 2. So that's a 0. I end up with 2. That's a 1. I end up with just pi. And you get, I'm sorry, it's negative pi over 2, so negative pi, negative 1 right here. That gives me my slope. And if I want to find the equation of the tangent line, I need the slope and I need the point. So now we see our x value is 2, our y value is 0. Point slope form is y minus y, or 0 in this case, equals the slope times x minus the x value. Distribute that, here's the equation of your tangent line. The slope of the other point where it crosses, t is positive pi over 2. So y minus 0 equals the slope, 2 over pi, right? Because you're plugging in a positive pi over 2, 0 here. That's a positive 1 there. You just get 2 over pi. And the slope times x minus the x value. And you get, the equations are similar, but they are different. So on the next page, I have all of these points plotted and the dots connected. Okay, so here we have the graph of what we just looked at. The values of t starting with the smallest and going to the largest. Always build your graph that way. Notice I left space between minus pi and minus pi over 2 and space here and space here, just in case I need more information from the interquadrantial angles. So plugging in the minus pi, we get x is 2 plus pi and y is minus 2 pi. That puts me way down here. And you see that as t is bigger and bigger negative, y is going to be bigger and bigger negative because the sign is bounded between minus 1 and plus 1. So we're coming from a very small, actually this is a little off. Let me fix this. We're coming from smaller values of y. Okay. And y just gets smaller and smaller and smaller because of this t. And then when t gets bigger and bigger, y gets bigger and bigger and bigger. Whereas the x value is just going to oscillate. The 2 is always a 2. So we're going to keep getting these points here, but the x value is going to go back on itself and come back. Well, later on in another lecture, we'll examine the behavior of this graph for larger values of t, positive and negative. But for now, let's stick in this little interval. So we have all of these values of t that we've plugged in, cosine is going to pop back plus 1, sorry, that's a minus 1, 0, plus 1, minus 0, minus 1. And then, of course, minus the negative is why you have plus pi. And then the y value was a little bit harder to calculate, but we did that on the last page. So let's plot these graphs here. We're starting down here, big negative y. We hit that point at t equals minus pi. The next point that we come to is at 2, 0. So you see how we're zooming up here. And then x is at minus about 1.14, and the y value is back at 0. So you see how we have a little hump. Now let's check and see where that comes from. Horizontal tangents are where dy dx equals 0. So taking the derivative of y, setting that equal to 0, I get the cosine of t is 2 over pi. But let's take that and plug that in to the x. 2 over pi right here. But if we look at the x equation here, if the cosine is 2 over pi and we multiply by pi, that's just a 2. So 2 minus 2, x is always 0 when I have a horizontal tangent. So you see, with what we've written so far, there's a horizontal tangent at 0 and minus 0. So we know, based on that when we're graphing it, once we get to this point and we're going to this point, that we have a maximum value there. And then as we're going from this point to this point, x goes back to 2, y goes back to 0. We have another horizontal tangent right there where x equals 0. And then the x value will keep oscillating and the y value will keep growing larger and larger that way. And you see the graph crosses itself at this point. We found that on the last page. And here I have graphed the tangents to the curve at those two different values of t. And because we have curves that are like this, you see that it's reasonable to have more than one tangent at a single point.